Decision theory models the choices we make against an indifferent environment. If you check the forecast and see rain, you grab an umbrella. The weather does not change its behavior just because you decided to stay dry. But human interactions rarely work that way. Most of the time, the environment you are navigating is made up of other people. This creates what economists call strategic interdependence. Look at a competitive environment like this chess tournament. You aren't operating in a vacuum. Every person in this room is calculating, reacting, and actively trying to outmaneuver the person sitting across from them. In these situations, your optimal move depends entirely on what your opponent decides to do. A brilliant tactical maneuver fails if your opponent anticipates it and sets a trap. To understand these reactive worlds, we have to stop looking at decisions in isolation. Instead, we have to deconstruct them into the strict mathematical components of what economists call a game. Think of a game as a blank mathematical sandbox. The first piece we need to place inside it is the decision makers themselves, the players. These players don't have to be individual humans. A player is simply any rational entity acting to maximize its own benefit. That could mean competing fast food chains, biological genes fighting for survival, or sovereign nations negotiating a climate treaty. Once we have our players, we have to give them the capacity to move. We define the specific choices available to them as their actions. Every time a player is forced to select one of these actions, they reach what we call a decision node. It is a precise point in time or space where a choice must be made. This logic model illustrates the timing of those choices. Sometimes players act simultaneously, making their choices blind to what the other is doing. Other times, the game is sequential, where players take turns and make decisions one after the other. But simply dropping players into a sandbox and giving them buttons to press just doesn't simulate a real conflict. Without a goal, they have no reason to choose one path over another. A setup with only players and actions is just an assembly of parts. To see how a conflict actually functions, we need to introduce a driving force. That driving force comes from our third component, payoffs. Without a clear reward or consequence at the end of the line, there is no conflict to resolve. We quantify these rewards using a utility function. This is a mathematical score that represents exactly how much a player values a specific outcome. Here is the defining feature of game theory. Your final utility score isn't determined solely by your own action. It is the result of your action combined with the actions chosen by everyone else. Consider the classic prisoner's dilemma. If we are both arrested, the number of years I spend sitting in a room like this depends entirely on whether you choose to stay silent or if you decide to betray me to the police. This brings us to the fourth and final component needed to complete our model, strategies. An action is a single move, but a strategy is a complete contingent battle plan. A true strategy contains instructions for every scenario, accounting for every potential action and reaction your opponent could take across the entire game. By defining the players, their available actions, the final payoffs, and the overarching strategies, we have assembled the fundamental anatomy required for a simulation. We now have the complete blueprint of the conflict. Now we just need to see how it moves. On paper, this is a clean, logical machine. Out in the real world, negotiations, market competition, and daily interactions feel chaotic and disorganized. Take a stressful situation like merging in gridlock traffic. From the ground, it looks like a loud, unpredictable mass of frustrated drivers, all competing for the same few inches of asphalt. This matrix shows how the emotional noise strips away when we apply our framework. We can map the conflict as a simultaneous normal form matrix or a sequential extensive form tree. The cars become players, the lane changes become actions, and the saved commute times become utility scores. Once we identify an opponent's available strategies and their utility function, we finally have the variables required for a formal calculation. The mystery of their future behavior is replaced by data we can actually use. Understanding the anatomy of a game gives us the map, but it doesn't give us the destination. Now that the game is built, how do we calculate the exact point where it gets solved?